Below the surface of the North Atlantic, where sonar pulses meet silence and steel nets draw lines through living water, an operation unfolds with the precision of a surgical procedure. This is not merely fishing, it's choreography, it's logistics submerged in salt water. It's a mechanized ballet where each movement, each tensioned line, each trawl deployment must balance biology with engineering in real time. Out here, the sea is a field, the cod are harvest, and the vessel, a floating factory tuned for biomechanical exactness. Cod trawling, when viewed from above, may resemble a net dragging through the ocean, but from the perspective of design, it borrows from the articulated logic of sugarcane harvesters, machines that operate with millimetric spacing between rows, modulating intake flow and adjusting their grip to avoid bruising the stalk. In cod fishing, the same principle applies. Nets must guide, not crush. Biomass must flow in, not collapse. Cod, alive and reactive, must be handled not as cargo, but as a system in motion, one that feels every shift in current, salinity, and depth. The net isn't just a tool, it's a conveyor of living tissue, and every adjustment in speed or angle is a calibration in survival. On board, the process doesn't slow. Once lifted from the ocean's grip, cod begin a transformation, not unlike that of harvested fruits in tropical agriculture. They must be cooled, but not too fast, stabilized, but not stressed, preserved, but still alive in their integrity. It's here that fishing intersects with refrigeration logistics, and where a single failure in temperature control can compromise an entire haul. What citrus harvesters face when their onboard pre-coolers fail, internal breakdowns, microbial risks, degraded quality, is mirrored at sea. Cod, like oranges, require a chain of care. Only this chain starts underwater, and there's more beneath this process than just comparison. The lifting of cod from deep trawl zones evokes mining more than fishing, not just for the depth, but for the segmented precision of movement. Like in a mine shaft where ore must be elevated through vertical conveyor lifts, each section engineered to reduce compaction and preserve the mineral's form. Cod are hoisted through nets designed with layered tension zones. These baskets don't just hold, they cushion, they respond. They allow flow rather than friction. In doing so, they protect the cod's body from the weight of the next one above, a biological constraint mirrored in structural engineering. But perhaps the most underestimated variable of all is the water itself. Salinity, temperature gradients, the depth at which trawling occurs, and the speed of the haul. Each of these must be constantly recalibrated by sensors and operators alike. Much like a high-tech harvester adjusting tire pressure to account for soil compaction, cod vessels adjust their systems to protect both yield and environment. It is a continuous loop of feedback and reaction. Every haul is a calculation. Every catch is a test of equilibrium between mechanical force and living biology. To fully grasp the intelligence behind this process, imagine a split screen. On one side, the tension zones inside a cod trawl net. On the other, stress dispersal diagrams used in underground or elevators. Two systems, one aquatic, one terrestrial, both engineered to transport fragile materials vertically under pressure. One hauls fish, the other, rock, but both operate on the same principle. Protect the cargo from the force of the journey. What happens beneath the waves, then, is not merely the beginning of a supply chain. It is a mechanical performance where biology, engineering, and logistics converge in silence. This is where the cold chain begins, not in the ice, but in the net, not in the hold, but in the tension. And once you see it, you'll never look at a piece of cod or a fishing vessel the same way again. It begins quietly, a haul lifted from the ocean, fish glistening under deck lights, motionless in the wells of the vessel. But inside these calm waters, a silent degradation can begin. When cod are stacked without consideration for water pressure dynamics, the lower layers endure the weight of the entire catch. Their muscle tissue compresses. Their organs rupture invisibly. In longer trips, the damage accumulates. with up to 14% of the catch downgraded before reaching port. This isn't waste due to spoilage, it's structural failure caused by overlooked physics. Unlike land cargo, live marine harvests don't tolerate static mass. Cod, like any perishable load with internal biological structure, require movement, not just of the vessel, but of the water around them. Without regulated flow, the fish become ballast. Every additional kilogram becomes a downward force, and every minute without compensatory circulation adds to the stress. The result is not visible damage, but biochemical compromise. Flesh that loses firmness, fillets that break on the blade, flavor that dissolves in storage. That's why modern vessels are abandoning static fish wells in favor of dynamic, buoyancy-regulated holding tanks. Inside these tanks, water is not still. It moves with a purpose. Designed with internal turbulence systems, these environments keep cod in suspension, not just to simulate oceanic conditions, but to distribute pressure evenly across the school. The concept borrows from a surprising source: hydroponic root chambers. Just as oxygenated turbulence helps prevent root rot in leafy greens, controlled agitation helps prevent compression trauma in marine catches. The system doesn't agitate the fish, it sustains them. The results speak in numbers. Vessels using turbulence-regulated tanks have reported up to 8% higher protein retention in cod after filleting and freezing. That's not just yield, it's structural integrity, preserved over thousands of kilometers. The flesh remains tight, the fibers stay bonded. The product arrives not just intact, but pristine. In an industry where freshness is judged not only by color and smell, but by tensile strength, this shift is redefining quality standards at sea. On the Norwegian coast, one vessel took the concept further. Its retrofitted hold became a modular system, not a single tank, but a set of linked buoyancy-controlled compartments. Each adjusts turbulence and temperature independently, depending on the density of the catch and the time since harvest. With this configuration, the downgrade rate in fillet quality was cut in half. That means more premium-grade cod, less waste, and fewer loads rejected at export terminals. There's a sentence used by engineers on board these vessels, a sentence that reveals how much this process has evolved. The cod isn't caught, it's carried. In a way, it's true. The moment the net rises from the sea, the work of fishing ends, and the work of protection begins. From that moment on, every decision is about pressure. How much, how long, how to balance it. In other industries, we talk about shock absorption, packaging insulation, or container stacking. Here, it's hydrodynamic suspension, but the principle is identical. Protect the product from itself, from the journey, from time. Because what's truly valuable isn't just the cod that reaches the plate, it's the cod that arrives uncompromised. Not bruised, not crushed, not lost in the margins of a statistic. A cod that was never compressed beyond its biology. A cod that moved not as cargo, but as a living unit within a synchronized marine operation. One net, one hold, one perfectly calibrated flow. From the moment a cod leaves the water, its biological clock accelerates. Every second matters. The cells begin to respond not to oxygen, but to the lack of it. Even in cold water, metabolic decay can start within minutes if conditions aren't controlled with precision. In standard operations, if cod are held for more than 35 minutes without continuous oxygen flow, the deterioration becomes irreversible. The flesh loses resilience. Enzymatic breakdown sets in, and the freshness, so often associated with color or aroma, has already been compromised at the cellular level. What seems like a simple wait becomes a silent transformation. Fish that appear intact are, in fact, already beginning to fall apart from the inside. That's why the most advanced vessels have redefined the concept of live wells. No longer just tanks filled with seawater, these chambers now function as controlled environments where chemistry, pressure, and respiration are all continuously monitored. The key innovation is microbubble injection, streams of microscopic oxygen bubbles infused into the water, increasing dissolved oxygen concentration far beyond natural levels. In some systems, ozone is added, not to disinfect, but to stabilize stress markers in the fish, reducing cortisol levels and slowing tissue breakdown. This technology has roots in aquaculture. It was originally developed not to preserve fish post-catch, but to reduce stress in farmed species during transfer. Now adapted for the open sea, it allows wild cod to experience a kind of buffered transition from trawled freedom to onboard containment, without triggering the cascade of biochemical stress that degrades meat quality. The system doesn't cool the fish, it allows them to breathe, because in the cold chain, timing is as critical as temperature. And sometimes, temperature itself becomes the problem. Over the past decade, researchers discovered that cooling cod too quickly, especially in the first 15 minutes after capture, can cause microcrystals of ice to form inside the muscle fibers. These crystals rupture cellular membranes, releasing fluids that are impossible to recover during thawing. The result? Fillets that look fresh but cook into fragments. The paradox is clear. Cooling protects, but rushed, cooling destroys. Preservation is not just about cold, it's about timing, oxygen, and flow. This understanding has transformed handling practices in high-performance fisheries. On the coast of Iceland, several processors now immerse freshly caught cod in controlled meltwater rather than applying direct ice. Meltwater maintains a steady temperature just above freezing, allowing for gradual cooling without triggering internal crystallization. At the microscopic level, this simple shift preserves the integrity of the muscle fibers, especially the myofibrils, the core structural components of fish texture. When these are preserved, the cod doesn't just look good. It holds together during transport, during filleting, and ultimately on the consumer's plate. There's a principle that guides these decisions. It's not just about catching cod. It's about managing its biology moment by moment, long before the word logistics even enters the process. Cod must be kept alive in its cellular rhythms, not swimming but breathing, not frozen but gently prepared for the journey ahead. And so, in the new era of marine cold chains, the first step is not a refrigeration, it is respiration. Not insulation, but circulation. The cod begins its route not on ice, but in breathable water, an environment engineered to delay the ticking of its biological clock, because freshness isn't a temperature, it's a timeline. And that timeline starts the moment the ocean lets go. Cod travels across oceans, but its true route is not drawn on nautical charts. It's traced through a sequence of engineering decisions, biological safeguards, and technological timing, all of them invisible, all of them decisive. What we think of as a marine product is, in reality, the outcome of a mechanical process as delicate and demanding as any in modern agriculture. Not just a catch, but a system. Not just a journey, but a chain of precision designed to preserve life even as it transitions toward consumption. The best analogy doesn't come from fishing, it comes from the field. Imagine a conveyor belt transporting tender root vegetables, carrots, beets, or radishes, through a mechanized harvesting line. These vegetables must be handled with gentle acceleration, protected from crushing, guided along pressure-sensitive pathways. The same applies to cod. In both cases, internal pressure gradients determine whether the product remains whole or fractures in transit. In both, movement is designed not just to transport, but to protect integrity. That is why cod logistics now share vocabulary with agronomic systems. Turbulence regulation, pressure dispersion, biological yield, smart containerization. Onboard vessels, algorithms now adjust tank oxygenation based on fish density. In transit, sensors monitor not only temperature but physiological stress indicators. One Japanese cold freight company recently introduced a dynamic atmosphere container system, adjusting air composition in real time to reduce transport shock in high-grade seafood. Their results show fewer cellular ruptures, brighter muscle tone, longer shelf life, This shift is not about innovation for its own sake. It's about understanding that biological products, whether grown in soil or caught in saltwater, respond to every step in the chain, from the net to the hold, from the hold to the port, and from the port to the final destination. Cod is carried not by waves, but by systems. Systems designed to think ahead, to anticipate loss, to prevent it. And in the end, what's at stake is not just taste or texture. It's the unseen integrity of something that traveled far, through conditions few ever witness, carried by machines that never stop adapting. The logistics behind cod are not maritime. They are mechanical biology, in motion, an orchestration of oxygen, timing, and human foresight. In this process, there are no shortcuts, only sequences, only calibrated movements, only the silent work of systems designed not just to catch, but to preserve what was caught. That's how cod reaches its destination, not only fresh, but intact, not only edible, but engineered to endure. And behind every fillet lies this invisible choreography, an industrial ballet that begins at sea and ends at the plate, without missing a single step.